I am Agung Trisetyarso. In this paper, we present the circuit design for measurement-based quantum carrier Lookahead adder, or for short MBKCLA. This paper is available now at arXiv. This work is in collaboration with Dr. Rodney van Meter, who is a faculty member of Environment and Information Studies at Keio University. Measurement-based quantum computation is a new paradigm for implementing quantum algorithm in cluster states. So the cluster state is a highly entangled state of qubits, which can serve as the universal quantum computation. So by subsequent single qubit measurements, quantum gates are affected on the logical qubits encoded in the cluster states. And in this scheme, quantum information propagation is driven by the pattern of measurement bases regardless of the measurement outcomes. Conventionally, we use these symbols. The red box represents the sigma y eigenbasis measurement, and the pink box represents the sigma x eigenbasis measurement, and the squared box represents the adaptive basis measurement. Adaptive basis measurement depends on the previous measurement outcomes. So in this Toffoli phase gate, there are two steps measurements, which means there are two depths. And in the case of CNOT, we have one step measurement or one depth. We will review later about this. Also in 2003, Rosendorf et al. Have successfully implemented the MBKC to the well-known federal Barenko-Eckert ripple carry adders, or for short VBA. So VBA adder consists of the input of the ripple carry adder consists of the 2n qubit registers and also n-1 ancillas. And there are three steps in ripple carry adders. Firstly, carry computations, and then followed by the uncarry computations, and finished by summation processing. Rosendorf et al. Shows that the resources for we call federal Barenko-Eckert MBKC circuit, the resources is about 300N, and the depth about 3N. The purpose of our work is to reduce the depth and also to reduce the resources of the circuit. So here we also present the design and the trade-offs between the depth and the resources. Here we will give a review about the space and depth trade-offs between abstract quantum computations and measurement-based quantum computations in the scheme of nearest neighbor architectures. Okay. So this is the abstract quantum gate. This is CNOT and this is Toffoli gate. In this CNOT, in this quantum gate, this allows the non-adjacent computation. So as can be seen here that there is one ancillas which is not used in the quantum computations. And also in Toffoli gates, there are two ancilla which are not used in the quantum computations. In the nearest neighbor architectures, for example, in exchange interactions, we use the swap gates to exchange the information between the ancillas. And this is the CNOT for the non-adjacent computation. So also as can be seen here that this is the Toffoli gates, and this is the in exchange interaction, and this is the Toffoli gates in measurement-based quantum computations. Okay. As can be seen from the previous slides, that we can say that qualitatively, the measurement-based quantum computation needs more resources than the exchange interactions. But as we will see that, okay, here, so in abstract or exchange interactions, the resources about 2 plus n qubits, and need 2n swap gates for exchange the informations. But the depth is 2n plus 1 or polynomial. Contrarily with the measurement-based quantum computation, which needs more resources, 15 plus 18 n qubits, but the depth is, it is very remarkable, the depth is constant, 1. And for the Toffoli gate, the resources is 3 plus nc plus nt qubits. Nc is the ancilla for the number ancilla between the control qubit, and the nt is the ancilla between the control and target qubit. This is the resources plus 2n plus nc plus nt swap gates. But the depth also polynomial. This contrarily with the measurement-based quantum computations needs more resources, but the depth is 2. Okay, this is just, I want to show the strength of MBQC. Next, the idea which will be involved in our works is, in this work is the logarithmic quantum carrier Lookahead adder. There are two types of quantum carrier Lookahead adder. Firstly, out of place and in place. The advantage of the KCLA, this quantum carrier Lookahead adder is KCLA, is the depth of this circuit is logarithmic. So the big theta is logarithmic. So this is the task of the out of place KCLA. The unitary in the KCLA we need the ancilla to perform the unitary transformation, but the in place we don't need the ancillas. And in quantum carrier Lookahead adder we need 3 networks to perform the carry status. Firstly, the general network computations. This is the equations to perform the general network computations, and the rounds of the general network is formulated by these equations. The symbol means the floor of log n, and T is the rounds of the of the general networks, and M is the number of the Toffoli gates need in every round of general networks. Next, we need the propagate network for computation to compute the carry value. This is the equation for the carry for the propagate network, and this is the formulation to obtain the rounds of propagate network, and also this is M. Similarly, the number of Toffoli gates in the rounds, and also carry network. This is the illustration of the KCLA. Unfortunately, when Draper et al. Published in 2006 about KCLA, they assume that non-adjacent computation is allowed, which is physically unrealistic. So, in our work, we can obtain the KCLA for the adjacent computations in MBKC scheme, and also we can as we see later that we can obtain the size as the function of the P, G, and C rounds. So okay, this is what I mean is this is for this yellow circle shows that the non-adjacent computation are allowed in KCLA. Okay. Now we propose the evaluation schemes for the algorithms executed using MBKC. The evaluation of logical quantum circuits involving first several points. First, the circuit depth. Secondly, the number of qubits used, including the input and the ancillas. And third, the circuit area. And here we have a conjecture that in every circuit, the resources of the qubits can be categorized in two points, two items. Firstly, the computational resources. So this is circuit. The computational resources, the blue, which is represented in this picture in the blue box, and the communication resources. The communication resources can be divided to the horizontal and vertical communication resources. The horizontal resources is implemented by the wires, and the vertical communication resources is by swap kits. And this is the formulation to obtain the size of the circuit. Vn is the number of logical qubits. B is the number of the rounds of the gate of type I. And Xi, number of gates of type I. Ri, number of lattice qubits in an I gate. AI, number of logical qubits in I gate, generally 1, 2, 3. And this term represents the horizontal resources for the circuit, and plus the last terms represent the vertical resources. And the optimal circuit resources is represented by these equations. And from the previous formulations, we can obtain the mathematical formulation for the circuit. So in our circuit, we obtain the pitch is 4, and the variable logical qubits, the parameter for the circuit is following: the width, the height, the area, the number of clustering operations, the circuit depth, and the size. This is for the out-of-place MBKCLE. And similarly, we can obtain for the in-place. And this is the circuit design of out-of-place MBKCLE. So in this circuit, as can be seen here, that the form is in Manhattan geometry, and the information flows is from left to right, as can be seen from this yellow line. So out-of-place MBKCLE consists of the five constant columns and also the carry computations. So in these columns, the depth is constant, and also in the last columns. But in the blue box, the carry stage computations, the depth is logarithmic. So it's the function of n. And also similarly, we can obtain circuit design for the in-place MBKCLE. This is the constant depth. Also in the middle, also there is the constant depth, and the carry computations, the blue blocks represent the carry computation, which is not constant. Then we can obtain the size and depth comparisons of various types of MBKCLE circuit. So from the previous table, it is already obtained that the resources for VBA MBKCLE is about 300N. Also and the depth is 3N. So MBKC VBA represented by this purple line, and the out of place, the resources of out of place MBKCLE as the following, which is in the red line, and this is the size of the out of place MBKCLE, and the in place is in the orange line. Now we move to how to optimize the circuits. So there are two steps. There are two ways to optimize the circuit. Firstly, by relaxing the Manhattan geometry, and secondly by retaining the Manhattan geometry. So retaining manual optimization by manual optimizations, we can optimize the circuit as the following. So in this optimization, we firstly put the ancillas inside the machine, and then we bend the network between the logical qubits as the following, as can be shown here. And then we remove the number of unnecessary subregister qubits. Secondly, we can optimize the circuits by using the graph states quantum carrier Lookahead adder. So a graph states quantum carrier Lookahead adder is defined by these formalisms. So Donos et al. Shows that we can represent every circuit by these formalisms. So for example, for the C naught, we call this by C naught 4. The C naught 4 can be obtained by the following formalisms. So in these formalisms, there is information about the resources, the input, the output of the quantum gates, and also the measurement pattern of the quantum gates. So this is the example of the C naught 4. This is the C naught 15, and this is called by C naught 39. So why it is different with the C naught 54, what I mean? Because in this C naught 39, or it is usually called by graph state computations, quantum computations. Here we allow the arbitrary entanglement between the qubits. So the entanglement between the qubit can be implemented not by wires, but also by not by wires in terms of cluster state, but only by these wires. And by that definition, we can obtain the in-place graph states quantum carrier Lookahead adder. This is the bird's eye of the graph states quantum carrier Lookahead adder. And if we magnify this box as the following, this is the propagate networks. And here we can evaluate the circuit. Firstly, we can obtain the entanglement operations of in-place graph states quantum carrier Lookahead adder, represented by these equations, and also the qubit resources after the adjustment of graph states quantum carrier Lookahead adder. So and then for short that we can also obtain the number of entanglement operations for the in-place graph states GS KCLA, and also this is the expression for the resources of in-place GS KCLA. Finally, we can make the comparisons of resources of various forms of in-place MBKC. So the red area represents the horizontal communications, and the green area just represents the vertical communications, and the blue area represents the computational resources, and last one, GCA KCLA, the yellow area represents the resources comparison if we perform the in-place KCLA. So conclusions. In this work, we can we obtain the circuit designs and depth space resources for several forms of measurement-based quantum carry locate adder. And also, the optimizations can be done by bending the network and removing the border between the rounds. And the optimization of the in-place MBKCLA circuit will change shape from the Manhattan geometry to the diamond-like form.